You gotta go visit the critical family.
Oh. All right, guys, page 31. What, like, so what you're gonna do? I think it's got like,
Oh, did you check mine, Mr. Yang?
oh, no.
Yes, I'm pretty sure this concept we have like before, like,
Right.
yeah, I'm pretty sure we taught it before the break night.
Yeah, I know, it's like.
You're just missing out if you're on but, do you want me to, do
It might be good. Yeah, just go ahead.
Okay.
Be okay, full credit. Today we're going to talk about log derivatives and derivatives of exponential functions. Now, we've learned natural log, and we've learned exponential functions e to the x. We talked about how we want to update our formulas so that we can account for the fact that most of your problems are going to have a chain rule portion to it. So instead of just e to the x being e to the x, the derivative of e to the u is now e to the u times u prime. It's basically the same thing. You're just replacing the x with u and then always multiplying it times u prime. And natural log of x initially is 1 over x, but we're going to say 1 over u times u prime, which is the same thing as u prime over u. So again, conceptually, we learned everything that we need to learn for our test. We just have to tack on additional derivative rules. But also, it's good to recall some of these log properties. The first is natural log of 1. What's natural log of 1? Yes, no, 0, okay? And what's natural log of 0? Undefined, yeah, because there's a vertical asymptote at x equals 0, right? We know that natural log graph looks like this, and it's not going to extend to the left of 0, so natural log of the negative number is also undefined. What's e to the 0? Good. Anything raised to 0 is 1. And e to the natural log of a and natural log of e to the a, these are both showing us that relationship between inverse functions, that if we insert a natural log into the exponential function, they're going to basically cancel each other out. So the only thing left is going to be a. And same thing here. If I insert an exponential into a log function, the natural log and this log base e and this exponential function that has base e is going to cancel each other out, leaving me with just a. And there's one more thing that's good to know is natural log of e. What's natural log of e? Equals what? 1, yeah. So we've learned exponential function base e, but there's also exponential function base a. So base a can represent bases of constants, bases of other constants, like base 2, base 3, base 8, base 10. They all follow a general rule. But let's start off with e to the u. We know e to the u is just e to the u, the original function, times the exponent's derivative. Now, a to the u is going to follow very much the same. I'm going to give myself a bit more room here. It's going to follow very much the same as e to the u. There just needs to be a conversion that needs to happen. It needs to basically convert into base e. So whatever that base is, it could be base 2, base 3, base 5. We're going to say natural log of a. That is going to get that conversion in place. But then after that, it's going to feel very much like e to the u. It's going to be the original function times the exponent's derivative. So original function, a to the u, times the exponent's derivative. So between a to the u and e to the u, the only difference is there needs to be a little bit of a conversion into base e, and after that, then essentially we're doing the same rule as e to the u, the original function times exponent's derivative. So here's an example. Find f prime if the function is 2 to the x plus 3e to the x. Now, we need to recognize 2 to the x. This is an exponential function. Exponential function is if you have a constant base raised to a variable exponent. So you can say f prime is equal to, and 2 to the x follows the rule for a to the u. So let's just follow the rule, right? So what starts off? This starts off as what? Natural log of 2 times 2 to the x times what? Times 1. So you can leave that 1 alone. You don't have to put that 1 down. I just want to, I always want us to look for that u prime, even if it is nothing more than the 1. And then 3 to the x is easy. It's just 3 times e to the x times 1, which is just 3 to the x. You don't need to include that 1 there. Okay, next up, we have log functions. Most often, we're going to see the one that involves base e, which is natural log, log base e, natural log. But we could also find derivative of logs of other bases, log base 2, log base 5, log base 8. They all follow that pattern for log base a. So natural log of u is just u prime over u. And log base a is also u prime over u, but because it's not base e, we need the conversion. So the conversion is going to look like this, 1 over natural log of a. So once we get past the conversion, then it looks pretty much like your natural log rule, u prime over u. So I want us to feel like, these look more complicated, obviously, than the ones to the right. But I want us to think that this is an extension from the rules that we already know, right? There just needs to be a conversion, either natural log of a or 1 over natural log of a. Once we get past those conversions, then we're almost looking at the same rule, right? Obviously, they're a little bit different here because we got to do a to the u instead of e to the u. But if we think of it in terms of, original function times exponent's derivative, then it's the same thing. And then these are actually the exact same rule, just u prime over u. What maybe gets a little confusing is remembering where that natural log of a goes. For the exponential, it's going to be in the numerator. For the log, it's going to be in the denominator. So what helps me remember where the natural log of a goes? I look at the remainder of the rule, right? Here, a to the u times u prime, or e to the u times u prime, I don't see any denominator. So because I don't see any denominator in the original rule, that helps remind me that natural log of a goes in the numerator. And here, u prime over u has a denominator component, and that helps me remember, okay, there's a natural log of a, but it's going to be in the denominator, 1 over natural log of a. So hopefully that helps. Okay, you guys want to try this next example? Find f prime. Your one rule, one term, you're going to use the log base a rule. Second term, you're going to use the natural log rule. See if you can find the derivative following the rules that we've gone over. Okay, let's check our answer, see if we're okay there. Log base 4 of x is 1 over natural log 4 times u prime over u, which is times 1 over x. And then 4 times natural log of x, the 4 is gonna stay in our derivative. Natural log of x becomes u prime over u, which is 1 over x. No need to find common denominator. Any questions? Okay, try the bottom of the page, see if you can get comfortable with applying these rules as well as rules that from previous sections. Okay, any questions, page 31? You guys have a moment. Okay, page 32. Okay, one last topic to go over, that is log differentiation. Sorry, I forgot, there's one last thing here we need to do. Log differentiation, is basically taking, a non-log function, so that's important, that there can't be any logs in it if we want to do log differentiation. So simplifying a non-log function using log property to expand before differentiating. So there's two uses for log differentiation. One is a convenience thing. And the second is where we have a workaround for a problem where the rule doesn't exist. So the first case is where we want to find a derivative for a function that requires or that uses quotient, product, or chain all kind of meshed together And rather than finding the derivative using those product quotient chain rules, we can have a workaround by turning this into a log equation. If we can turn into a log equation, then all of a sudden we have all these properties available to us to expand out. The good thing with this method is it allows us to separate a messy problem that requires product quotient or chain rule or a combination of them into individual smaller problems that we can just using log properties to separate them. And then we can just individually tackle the derivative for each of them a lot easier. The potential negative is that your derivative looks like a mess. It just looks like something that you don't want to try to clean up. And if you're ever asked to do log differentiation, you're not going to be asked to clean up your derivative, but you just be prepared that it's going to look really messy. But it's a good skill to know. And then we'll talk about this other method or this using log differentiation for a type of problem where we don't have a derivative rule for. Okay, so here are our steps. First, we're going to take the natural log of both sides. And then we're going to look to simplify and expand using log properties, whether it's power property, product property, or quotient property. Okay, so let's take this one step at a time. So our first step, we're going to introduce logs into our problem. So take the natural log of both sides. Again, if there's already logs in the problem, we don't want to do this because if we add on another layer of logs, it just makes the problem even more complicated. We're never gonna, if there's already logs in it, then we just start the problem. We only do this if there's no logs at all. And now that we've taken logs of both sides, we now can use some properties, right? This is basically natural log of A over B, and I can take advantage of my quotient property and basically split them up into the difference of two logs, right? So natural log of A over natural log of B equals natural log of A minus natural log of B. So I'm going to take my numerator and denominator and split them up into two separate natural log expressions. So already we're dealing with an easier problem because something that was initially one connected mess is now broken up into two smaller terms. Okay, question so far? Now, we don't want to find the derivative just yet because we would prefer not to have these exponents here. If they were there, we'll have to go through chain rule, and we want to try to avoid that layer chain rule. So what can we do with these exponents? Bring them down, right? Because we have another log property that tells us that as long as we're inside a log term, that exponent is free to move, right? Either move it down or move it up, depending on what helps with your problem. In this case, it helps if we can get those exponents down. So we bring those exponents down. And now we have three individual problems that are much easier to handle because we also include what's on the left side. The left side was just y, but now it's natural log of y. So we have to go through a little bit of implicit with that term. So we're going to find the derivative of each of these terms. All those rules are just u prime over u. So let's go through this one at a time. What's the derivative of natural log of y? Good. So we know y's derivative is 1, u prime over u, which is 1 over y, just like how we do natural log of x is 1 over x. But because we're asking for y's derivative, we need to include a times dy dx. Okay. And then what's next? Equals what? 2 natural log of x minus 2 becomes what? The 2 stays, right? But then natural log of x minus 2 turns into what? U prime over u, so 1 over x minus 2. And then we keep going forward, 1/2 stays. And then we do u prime over u for natural log of x squared plus 1. What's u prime? 2x over x squared plus 1. Good. So we have our derivative. And now it's just how do we clean this up? Now, what's our goal? Our goal is to, yeah, that dy dx, right? We want to just get that dy dx by itself. So what needs to move? The y, yeah. So that y is going to end up where? That y in the denominator on the left is going to end up on the right side as a what? Numerator, good. And then I'm going to just do slight cleanup with my fractions here. We don't have to. As long as you get dy dx by itself, that's really all I'm looking for. Now, there's one more thing that we can do. We're trying to find the derivative of y with respect to x. This is a function. Okay, so we're starting off with a function. We're just using implicit differentiation as a way to move through the problem. So we shouldn't have to keep that y around. Is there a way to replace the y? The original, yeah, we can go back to the original function. We start out with a function, so we should be able to represent our derivative as a function as well. We shouldn't deal with y's unless the original equation doesn't pass a vertical line test. But this is fine because everything is defined in terms of x. This is a function, so we should be able to represent our answer as x's. So with log differentiation, as long as you have your derivative terms there, you don't have to worry about cleaning it up or common denominator. It's just going to be a mess, and that's fine. Any questions? This is a good skill to know. You're going to be tested on it with log differentiation, but on the AP exam, if log differentiation shows up, it usually shows up as this second example, which I'm going to go through. Okay. But it's still good to know, and you'll still be tested on it. But just to kind of give you an idea that, log differentiation typically is not a major topic that shows up on the PC exam, but if it does show up, the second example has higher chance of showing up. So let's go over that. So here's example 2. It says find the derivative of x to the 2x plus 3. Now, if we look at this, we don't have a rule that can handle this setup. I can do a variable raised to a constant, that's power rule. I can do a constant raised to a variable, that's exponential rule. But if I have a variable raised to a variable, we're kind of stuck, okay? We don't have a rule that can handle that derivative. So the workaround is if I can somehow get that variable to come down as a coefficient, then I have more rules that are available to me. So this is where we have to use log differentiation to allow for that exponent to move, because right now we can move the exponent without changing the overall value. So if I have a variable raised to a variable, the workaround is let's force it into a log equation, and then we can use log properties to move towards rules that we can actually apply. So we'll do natural log of both sides. Now that I am inside a log expression, what property can I use? Yeah, bring down that exponent. I want to protect that 2x plus 3 with a set of parentheses so that I remember that when it comes down, it's going to be a connected expression. So I want to find a derivative. Left side is just what? Good. Same thing, right? 1 over y dy dx. But the right side, what's involved here? Say it again? Product rule. Yeah. So whenever you see a variable raised to a variable, and you're getting ready to take log differentiation, just be prepared for the fact that product rule is going to show up. Okay, so you can expect product rule to show up for this type of log differentiation because that variable coming down is going to force 2 different expressions being multiplied, and that's going to have to go through product rule. Okay, let's try that. See if you can go through product rule. We can compare our steps on this. So we know left side is one over y dy dx. We go to the product rule, f prime times g plus f g prime. Don't have to clean up your expression, but we want to solve for dy dx, so what needs to come over? Y, and then replace the y with what? Yeah, the original expression, yeah. And then you leave your answer in any form. I'm not looking for any, you don't have to worry about simplifying, making the problem look a certain way. As long as all your pieces are there, and then your right side is in terms of x, that's all I need. You don't have to get it into a specific form. And so I have the x and the product. So I split them up into two fractions, and once I'm sitting at two fractions, they're independent of each other, and I cancel it out. But you can leave your answer in this form. Just make sure you're putting the y back in that. Question. So I would like to use the rest of the class just for me to kind of help pace you through some of your homework problems. We have about 15 minutes, so I'd like for us to get started with the homework, and then we can kind of go over them and use that as classwork as well, but you're also moving towards getting your homework done. So this is from your textbook page. So go ahead and start with 31. If you need scratch sheet, I have them, but if you have notebook, use that as well. Oh, I just thought of something here. If you're asked to find a derivative involving logs, let me change. I just want to show a couple, two things. Let's say both these problems are asked to find a derivative. Whenever I see a log problem, I'm always thinking, okay, the log expression, how can I take advantage of log properties so that I don't have to deal with a messy product chain rule combination? And here, if you look, this is in the form of natural log of A times B. I can expand it into y is equal to natural log of A plus natural log of B. And that comes down, it becomes a lot easier to work with. Right, and now it's easy, right? U prime over U, that's my derivative. So anytime we see a log problem, think about how can I use expansion properties so that I can make my derivative process a lot easier. But that's most problems. But what's wrong with this one? Can I use log properties here? I can't. I don't have a rule for natural log of A plus B. This is not the same thing as natural log of A plus natural log of B. This is inside the log term. We can't distribute unless this is a standalone term, but this is not. So we can't do that. The rule is natural log of AB can be expanded as natural log of A plus natural log of B, but natural log of A plus B is stuck. We can't do anything. So if you see a problem like this, you're forced directly to go to U prime over U. There's no expansion you can do. So this is your U value, and you just jump into U prime over U. The answer will be messier, but we're kind of stuck. We can't, that plus messes everything up. We can't use properties like we can here. So I want to make sure that you guys can see that distinction and that we don't misinterpret expansion properties. All right, so go ahead and try 31. And looking at 31, that's what reminded me of the fact that we can't use this property like we would like. So, yeah.
I know. Like,
Okay, all great. I'm happy, yeah, thank you. Yeah, you have to keep it in the numerator portion. Oh, so you just do the one over anchoring it, so you can't move, and that's the common denominator, and I agree that denominator. Oh, right. For some reason I dropped that little chain rule for some good point. Yeah. And these spots we do. These phone calls, anytime. See if we can spend about 10 minutes making progress with our homework.
Let me know if you have any questions.
Would you? So I said that here.
So I think
So inverse tangent is u prime over 1 plus u squared. The derivative of natural log vector for the
How do you get outside? You also have to multiply it again by 1/x.
Well, the outside is my inverse tangent. My inside is my natural log vector. So think of whatever's inside here. This is my u value. So the derivative of natural log of x is u prime over u. So 1 over x times 1. So that's the nested portion back here.